Good afternoon. My name is Qiyue Qian. I'm a third-year PhD student from Tsinghua University. Today, I will introduce the systematic search for the free-floating planets in KMTNet microlensing survey, and my collaborators are listed here. So microlensing makes it possible to detect faint isolated objects, such as free-floating planets. And due to the low mass of the free-floating planets, their microlensing events can have extremely short time scales, typically lasting less than 1 day. And their angular Einstein radii are only at the level of micro-arcsecond, which are comparable to the source stars. So as the example shows, they tend to show finite source point length effect. So the detection and the constraints to the FFP events requires high cadence surveys. So KMTNet is one of the high cadence microlensing surveys. It has 12 square degree high cadence fields and regularly operated for 8 years since 2016. What's special is that its 3 global sets at South Africa, Australia, and Chile provide nearly continuous observations within 1 day. So it intrinsically has an ideal coverage for the short timescale events. For the bound planets, KMT shows a great ability to detect the low mass ones. But for the FFPs, the lowest theta E of KMTNet is around 5 times larger than that in Moi and Ogo. Because the theta E is proportional to the square root of mass, this implies a more than 20 times mass gap. That is contradictory to its sensitivity on the low mass bound planet. So where are the low mass FFPs in KMTNet? To understand the tension, we have to look back to the workflow of KMT. And the previous KMTNet image process has 3 steps. First, they use the FIDI pipeline for the full-frame photometry and use the event founder to search the microlensing events. In this step, the photometry is not so accurate but fast enough for the real-time reduction. Then they cut the stems around the detected events and use the pySIS to produce small preset cycles of these events and search for the planet anomalies on these events by anomaly founder. And for these anomalies, they reduce the image again by pySIS turnaround Chi, which is improved recently by Hongjin Yang. And this step can produce the most precise and stable cycles. The pipeline is sensitive for the bound planet detection because the microlensing signals of their host stars typically last for tens of days, which can still be detected as a new event in the first step. But what if there is no peak of the host star? Due to the imperfect image reduction and photometry on the first step, the scatters on the light curves can be confused with the short timescale signals. And the FFPs, especially the low mass ones, may be buried in the noise. So to detect the potential FFPs missed by KMTNet, we are trying to set up a new full-frame photometry pipeline based on pySIS updated by Hongjin. And this pipeline will not only process the detected events, but all the potential sources. So the first step of the full-frame photometry pipeline is to register the frames because the precision of photometry center will influence the sensitivity. We improved the cross-match algorithm to make the frame register more accurate and robust. The residuals after the register are shown here. The precision error can be reduced to less than 0.1 arcsecond, which is a quarter of pixel size of KMTNet. Then we mask the non-bad pixels, variable stars, and saturated pixels to avoid their influence, as the green circles here shows. And we still cut the full-frame images to stems so that the PSF and the sky background can be more uniform inside them. And these stems will overlap at least 60 pixels to make sure the stars in the edge can be well processed at least once. And finally, we apply the pySIS on the stems to conduct the image subtraction and lacquer extraction. Compared to the previous result, the scatters in the lacquers from our new pipeline are much reduced, as you can see. And if we add simulated events on the baseline from both pipelines, as you can see in the previous pipeline, it will confuse with the noise. But in our new pipeline, it will be much clearer, so you will discover it immediately. So currently, we have tested our pipeline in 1 year, 1 square degree KMTNet images and extracted the stars brighter than 17 magnitude. We got nearly 500,000 effective lacquers in total. And we preliminarily searched on this lacquer sample. We set up the threshold here to automatically select the non-constant stars with significant bumps. And then we matched them with non-OGO variable stars and remove them from our sample. Only 0.8% unknown stars will remain in this step. And we visually check the remaining lacquers and select the microlensing lacquers. This step only costs around 2 hours, which is not a heavy work. And to further check these lacquers, we match them to the previous events, and for the unknown events, we checked their images and the multi-year data. These 50 microlensing lacquers, including 25 non-KMTNet microlensing events, and 6 non-OGO and more events but missed by KMTNet in the previous search. And for new event candidates, we also found some false positives due to various reasons, such as asteroids and image problem and some variable stars or flyers that is confusing. These events includes both in our catalog source and the nearby sources. So here I show an example of an OGO microlensing event. And this is actually the window for my visual check. The left panel is the binned lacquer, and the right panel is the zoom in for the region of variability. This event is missed by the previous KMTNet search, but recovered in our new pipeline. And there are some new microlensing candidates with low amplitudes or short time scales, including a binary event. So also we found some extremely short timescale signals, which is very similar to the FFP events, But after checked the multi-year data, we found a previous signal that shows a significant flyer or CV features. So we consider it not an event caused by FFP, but or a variable star or flyer. Although we have not detected any FFP candidates in the current sample, the detection of the other short time scale signals still shows that our pipeline has enough sensitivity for the FFP detection. Okay, so currently we have set up the new full-frame photometry pipeline for KMTNet and greatly improved the photometry quality and the sensitivity for FFPs. We have tested our pipeline in 1 year, 1 square degree images, but not detected convinced the FFP yet. However, we recovered 6 OGO and more non-events that is missed by the previous KMTNet search and detected 4 new microlensing event candidates. Next, we will submit the results for this 1 year, 1 square degree result and calculate the detection sensitivity. In the future, we will reduce more fields and years of KMT historic images. We plan to finish the 8-year, 1 square degree photometry and the search in this summer and finish all the 8 years 12 square degree high cadence field search before the next spring. So hopefully we will find some new FFP candidates, especially the low mass ones, and get mass function results finally. So that's all. Thank you.